Hi, everyone. I'm Laura Bruckman, and I'm a professor at Case Western Reserve University in the Material Science and Engineering Department. And I want to talk to you about a project for the MDS-Rely Center. And this is a netSEM modeling for the service life and prediction of acrylic polymers. So point of this project would be to develop study protocols that allows us to perform materials data science on polymers and therefore determine the service lifetime prediction, capture more information about these polymers, and then model their behavior in data-driven models or network models. So what we want to be able to do is develop models for lifetime prediction of acrylic polymers. I've decided on acrylic as a good proxy material for doing these studies and looking at service lifetime prediction, but the IAB could change this polymer if there was consensus that they was a more interesting polymer for the group. So what we would do is do data-driven modeling, network modeling, and cross-correlation of multiple stress conditions. And this methodology would allow us to extract greater scientific information and insights about these polymers and how they degrade. So it allows us to use standard exposure conditions plus additional exposure conditions to identify failing and also to identify failing materials early in testing. So this allows us to improve the material science data and codes that are available around doing degradation modeling. So this project is leveraged by our netSEM R package that was originally developed with UL funding and then has been further iterated and improved under DOE CETO funding. So these network models, netSEM, are based on structural equation modeling, but they've been modified so that we can have much more practical functional forms for how these degradation mechanisms occur. And this gives us a system of equations in which we can model the behavior of a material and how it changes under different stress conditions. So the figure here shows, in this case, an example of a Tenevin stabilized acrylic polymer. And there's a radiance and temperature as stressors, and they both cause Tenevin bleaching as well as chain scission, which are the two green boxes. And as the Tenevin is bleached, those cause chain scission and leads to mechanical degradation in stage 2. And in stage 3, that leads to a modulus change or basically failure in this acrylic material. So we want to develop these network models that allow us to understand the relationships between stressors and responses or performance with a good understanding of the mechanisms that are occurring within those polymers. This will give us improved study protocols to be able to predict the lifetime of these materials and also do it in a larger parameter space when we're considering stressors. So this would require us to have a very developed study protocol, and this is multiple different exposures, standards out there, as well as modified standards or real world conditions that have multiple stressors. And then we also want to use multiple replicates. We want a population-based study so that we can understand not what's not happening to one material, but how is the variance in their behavior over time. And we need to take data frequently through the exposure and extend it out beyond just, say, the pass-fail requirement for a material. So I'm going to show you a couple examples of data-driven models and network models with PET. So this is 3 different grades of PET and 4 exposures, and we developed these fixed effects models, which you can see here for yellowness index. And then we also were able to model all of these materials' performance under all different exposures together. And then we can just slot in, hey, we're choosing a hydrophilically stabilized material versus a UV stabilized material, and here's what we predict the YI to be. These are more data-driven models of different types of PET. And here we're looking at accelerated versus outdoor. And we did dry, full spectrum UV, wet full spectrum UV, and we also fleeted these out in Arizona and Florida. And what you see is that in PET, there is an incubation period in which we don't get a lot of color change. And then all of a sudden we see rapid color change in these wets. So this allows us to understand that mechanistically, there's something is occurring. And then once there's a certain buildup of a byproduct, then we can start forming yellowing. And this is only occurring under hydrolysis. What we also see when we're talking about cross-correlating and making sure that we're understanding the lifetime outdoors as well as not just under accelerated exposures, is that Arizona and Florida actually have very similar behavior. And we had assumed that Arizona would not because it's dry. But what we're surmising here is that, in fact, water sitting on these materials outdoors plays a key role as morning dew. So here's an example of netSEM. So in this case, this is PET exposed to the same condition with and without water spray. And what we see here with just FTIR peaks, looking at the mechanisms, we see only two degradation mechanisms. We see a carbon-oxygen cleavage, and what we kept seeing is this clean PET peak, that we are seeing in the FTIR. But when we did this without water spray, we got lots of peaks associated with the different degradation products. And what we decided was this indicated that on the sample with water spray, we were actually washing away the degraded surface of our PET and getting new nice PET forming. So what we wanted to do is this confirmation. So we wanted to confirm that that was actually happening. So we used excitation emission fluorescence spectra and then did parallel factor analysis on it. And we took water and took a spectra, and obviously there's nothing fluorescing in DI water, but then DI water, when we immersed that PET film, started fluorescing. And actually we were able to model with parallel factor analysis that we were able to model the monohydroxy and the dihydroxy substitution of the terephthalate ring and how much relative they were there. And we've done this in other studies with PET films. So we want to make sure we're confirming our mechanisms. This could include size exclusion chromatography, solid state NMR, etc. And then for the deliverables of this project, we would want to develop a performance data set, have data-driven and network degradation models, as well as resulting code to develop those models. And then our tasks would look like we would determine what types of acrylic and what exposures we're interested in doing, and then perform those exposures and evaluations, and then do our data-driven and network modeling, and then also be able to do service lifetime prediction under various stress. So within that parameter space of multiple stressors. So thank you very much, and I appreciate you listening.